So in this problem, we're asked to once again figure out when f is increasing and decreasing, but we're given the additional task now of finding a relative extrema. Hopefully you read in the notes about the first derivative test, which lets us figure out when we have a relative max or min, when our critical points turn out to be a max or min, because we're going to be using that here. First steps, same as before. To talk about increasing and decreasing, we need to know the derivative. So we go ahead and find the derivative, and we can do that pretty quickly, again, since we have a nice little polynomial here. And then we want to know when the derivative is 0 or undefined. Just like the previous example, undefined is not going to be a problem here because we're dealing with a polynomial. So it's undefined is not going to be a problem. So we just really need to figure out when it's 0. Okay, so setting it equal to 0, I went ahead here and factored out a 5x squared, common factor. That left me on the inside with 2x squared minus 3x plus 1. And so we can solve when is 5x squared equal to 0. That'll happen when x is 0. And then when is 2x squared minus 3x plus 1 equal to 0? You have a couple of options here. You could factor this one. It actually does turn out to factor by grouping. Or if you wanted to use the quadratic formula, you could do that. In either case, you're going to come up with two examples here, which is x equals 1 and x equals 1/2. F prime, of course, as we already discussed, is never going to be undefined. If you check the notes for this problem, it's the same problem, and I did do that with the quadratic formula. So if you want some little practice, you might want to do that on your own, just to kind of practice that idea. So at this point, we have 3 critical points, 3 values of interest, 3 places where my derivative could elect to change its sign, but maybe it won't. So plot all 3 of those values on the number line, and then notice how that divides our number line up into 4 sectors. So the behavior of f, as far as increasing and decreasing, can only change when it switches from one of those 4 sectors to another. So at this point, we need to test values. So I pick something smaller than 0. So in this case, I do f prime of -1. And when I plug that in, I get positive 30. That means below 0, the graph of f always has a positive derivative, and therefore will always be increasing. Always be increasing. I need to pick something between 0 and 1/2. Anything between 0 and 1/2 will work. I picked 0.25. And when I evaluate that back into the f function, not the derivative, the f function. I'm sorry, I said that wrong. Plug that back into the derivative, not the f function. I knew what I wanted to say and said it wrong. We'll get that it's about 0.117. So in other words, it's actually still positive. So at 0, the derivative actually didn't change sign. And in something between 1/2 and 1, 0.75, I get about -0.35. So it has now switched, and now we have the derivative being negative. And then something above 1, I just picked 2. And when I plug 2 in, I get f prime of 2 is equal to 60. So it's actually has resumed increasing. Then I'm just going to do a little bit of color coding here to indicate when it's increasing in blue and when it's decreasing in red. Okay, and so at this point, we're ready to answer the question of when's it increasing and decreasing. So let's go ahead and do that and get that out of the way. So all those blue intervals, I'm going to write down as increasing. So that's from -infinity up to 0, but not including 0. And then from 0 on to 1/2. Skip over the 1/2 to 1 because that's red. And the interval from 1 to infinity. And then decreasing just happens to one place there between 1/2 and 1. Okay, and so if that's all we wanted to do was increasing, decreasing, then we'd have that and we're done the problem. So now we turn to the problem of relative extrema. And here's the good news. Based on all the work we've already done, we just need to take and use the work right here, this sign chart, and understand it. That's what the first derivative test is about, to figure out when we have any relative maxes or mins, if we have them. If we have them. And so notice here, obviously here it's positive, positive, so that's not going to be anything. It continued increasing. But here we have it increasing until we reach 1/2 and then decreasing afterwards. And so that's the behavior of a relative max. A relative max. So as long as f is defined, not f prime, but f is defined at 1/2, that's going to be a relative maximum force. That's going to be a relative maximum for us. And likewise, at between 1/2 and 1, it's negative, so it's decreasing. And then when it switches over, it's increasing, and that produces force of valley. So as long as f is defined, f, again, not the derivative, but f is defined at 1, then we're going to have a relative min there. And so to finish this off now, we just realize, hey, I have a relative max, as long as it's defined. It turns out it's polynomial, so it's defined, at f of 1/2. And where does 1/2 go? Well, let's evaluate the function, not the derivative now, but the function f, to get our point. So when we plug 1/2 in, that comes out to be about 0.0365. So that's going to be my relative max on the graph. And then the other point there at 1, that's going to be a relative min. And so we can write that out. F of 1 actually comes out to be negative 1/12. And so that's our relative min. Okay, so at this point I want to quickly take a look at the graph of this function and show you how we've found the different pieces of the graph. You can see the graph is increasing until we reach 0. Notice at 0 the graph levels out, but it doesn't actually turn around, it just keeps going, it resumes going up. And so we have here our relative maximum at 1/2, 0.0365. All right, and then the graph starts decreasing for its first time between 1/2 and 1. When it gets down to 1, it reaches its relative min, and then the graph resumes increasing. The graph resumes increasing. Now, I wanted to look at the graph to show you that information, but also to show you how the derivative comes into play here. How the derivative, so I have the graph of the derivative function here. And so the derivative is positive until we hit 0. The derivative then bounces up. That's when the graph resumes its increasing behavior. The derivative reaches a maximum point. And if we kind of zoom in here on the graph, when that derivative reaches that point at around 0.3 there, I do want you to notice something about the shape of the green graph. When we cross that 0.3 part, the graph kind of is like kind of curving up like right here. But now once you pass a point around 0.3 there, the graph's now kind of curving, has a down type curve to it. We're going to talk about that in the next section. That's called concavity. That's called concavity. Okay, so we'll get into that, talk about that in the next section. But here I would just want you to see here, once the derivative hits the negative point, crosses over, you can see my function here goes decreasing. And then when the derivative finally crosses back over, my function is, again, reaching that relative min and turning around. Okay, so hopefully this helps you out as you kind of see the connection between increasing and decreasing in relative extrema and how the first derivative comes into play.